Okay, so yesterday we used a notion of hyperbolicity, the delta hyperbolicity or Gromov hyperbolicity. And today I would like to introduce another notion of non-positive curvature, which is cat-0 condition. So if the delta hyperbolicity, I defined it in terms of condition on triangles, the delta sin. And here, again, it's a definition in terms of triangles. So again, X is a geodesic metric space. Geodesic. So you take 3 points. And geodesic means I have some segment. So I have X, Y, Z. So I look at the distance between X and Y, Y and Z, and X and Z, and I construct what is called the comparison triangle. So in the so here it's a picture in X, and I have a second picture in R2, the Euclidean R2, and I have my comparison triangle, which is a triangle X bar, Y bar, Z bar, such that this Euclidean distance is the same as this distance in X for each side the same. Okay, so I have my 3 distance. I construct a triangle with the same distance, and then I take 2 points on the side, on 2 different sides, say U and V. And again, I can put the comparison points here, so that this distance in X is the same as this distance in R2. So I have my comparison point U bar, and the same with V bar. And we say that X is a cat-0 space. So X is a cat-0, where C, A, T are for Cartan, Alexandrov, I guess, and the T is another Russian mathematician, I forgot the name. Topogonov, okay. So it was the name proposed by Gromov, I guess. And so that's the CAT. And the 0 is because we compare to the 0 curvature case. So you also have a version of cat1 or cat-1 if you compare to the sphere or to the hyperbolic plane. Okay. So here I will use cat-0 because I compare to 0 curvature. So X is cat-0 if for any triangle, so for any X, Y, Z, and any U and V on the side. Okay, so U and V are, U is on the segment X, Y, and V on the Y, Z. You want the distance computed in X between U and V. You want this distance to be less or equal than this distance. So the distance in R2 of the comparison one. Okay, so in some sense, the triangle in X are thinner than the comparison triangle, maybe equal. Is it okay? Yeah. Okay. So it's different. So for instance, for sure, so maybe examples here. No. So first example, R2 is cat-0. So you admit some zero curvature. You're okay with that. So R2 is cat-0, but not delta hyperbolic. Okay. So the example of delta hyperbolicity is if you take a tree. Okay. So for example, take an infinite tree with a valence 3 at each vertex. So, okay. It's supposed to be infinite. So this will be delta hyperbolic and cat-0. but I can break the cat zero condition by putting some small loop, so a small triangle here. So at each vertex, I put something like that. Then you will, because of the cycle, you can check that you break the cat zero condition, but you don't break the delta hyperbolicity, just you put the delta larger than my small triangle. It's going to delta hyperbolic for this small delta, but it will not be cat zero. Or okay, maybe to be even more, you can attach if you want a small ball so that you really see some positive curvature. Maybe it's better like that. So attach a little ball at each one. Yeah.
Delta hyperbolic is something like large scale.
Yeah. So delta hyperbolic is like a tree. So it's very hyperbolic, but from far away. And so at small scale, you don't ask for anything. And cat zero is maybe it's flat, but it's at every scale. So even at small scale, you want to see the negative or curvature. So it's not the same condition. And the good property for cat zero space is that you have good fixed point property. So let me give one. So in fact, fact in a cat zero space, if any bounded subset admits a circumcenter. So it's like in the case of a tree, circumcenter is the center of the unique ball or the unique smallest ball containing your bounded subset. So because of this notion of center, unique center, you have some fixed point property. For instance, a very easy one is if you have a finite group acting by isometry on such a cat zero space, there is a fixed point. So consequence of that, any finite group acting by isometries on X cat zero admits a fixed point. Which is not the case for delta hyperbolicity, because you could miss, for instance, you could imagine that you rotate such a small sphere, but the center is not in your space. So you have no fixed point. So maybe let me try to put a kind of qualitative picture here of what we can expect with the two notions. So you have delta hyperbolicity on one side, and you have cat zero property here. So we saw yesterday that when you have an action on a delta hyperbolic space, if you have if you find an element which is loxodromic with this extra property, the WD property, you can try to apply a small cancellation. And then you produce normal subgroups. So this is really a feature of delta hyperbolicity. And for cat zero spaces, you have a fixed point property. And you can try to classify a finite subgroup. So it's more a feature of acting on K0. And then if you want to prove the Tits alternative, I mentioned in the first lecture, you need a little of both in some sense. So Tits alternative should be alternative. So you want something K0, but you want also, yeah, so I have this picture in mind. For the Tits alternative, you would like to have an action on K0 space because if you have a fixed point property, for you have your group you want to understand. If it admits a fixed point, then you reduce your question to understanding the stabilizer. And in the space I'm going to construct, for instance, my stabilizer are going to be a semi-direct product where one part is linear, so we know this alternative, and the other one is going to be solvable. So it's what we want to prove for Tits alternative. Okay, so if you have fixed point property, you reduce your question about subgroups to smaller subgroups, the stabilizer, so you have a chance to say something. And if you don't fix anything, then you would like to prove, so the alternative in this alternative, you would like to find a free group over two generators. And that the standard way to produce free groups is to use a ping-pong argument. For ping-pong argument, it's more on the delta hyperbolic side that it's easy to do. So when I did it for my action on a tree on the first day, the tree is perfect because it is K0 and delta hyperbolic at the same time. Everything works fine. So the problem, now I would like to prove something similar for Tame K3. And the delta hyperbolicity was good for normal subgroups, but my space of triangles is not K0. So we did a trick. We put some negative curvature on each disk by putting some correcting term. But the problem is that I don't have a uniform way to put my correcting term. It's just when I have the disk, I explain how I change the angles. But if this triangle belongs to another disk, maybe I don't do the correction the same. So I don't have a uniform way to put a K0 metric on my triangle complex. So I'm going to construct another space where I have this K0 property, but I don't have the delta hyperbolicity anymore. So at the end, the finite subgroup I will understand, and the Tits alternative, well, we managed to do it, but it's complicated because we have two spaces. Okay, so let's start with my second construction. So the first one was a triangle, or even the simplicial complex for Tame Kn for any n, any k. So here it's going to be similar. I start with the construction for any k, any n. And I will specialize after that to dimension 2 or 3. So all of that is in a paper with Piotrzytycki again. It's a paper, so the construction is the first paper published in 21, and then the Tits alternative is in a preprint, more recent preprint. Okay. So the idea is to, so for any n and for any field k, we're going to construct an action of the group of Tame automorphism on a space of valuation. So on a subspace of the full space of valuation. So it acts on all valuation. I'm going to mention it, but the point is I'm going to choose some particular valuation so that I can put a nice metric on it, which will be K0. I don't know how to do that on the full valuation space. Okay, so let me recall first what are valuations, what are the valuations I'm going to consider. So I look at valuation on the polynomial in n variable. So a map new from k x1 xn to r, and I admit also infinity value is a valuation. If, so you have the familiar property for the sum and the product. So for the mu of P1 plus P2, it's more than the minimum of the valuation at P1 and at P2. Minimum. And the valuation of the product is just the sum. Okay, so that's the main, two main properties. And then by convention, I'm going to ask also something for constant. So I ask that mu of a polynomial P is 0 for all P constant, non-zero. And the value infinity is just for 0. So, okay, so the zero polynomial at this special value. The constant goes to 0. After that, the two properties. Okay. So let me give you some examples. So if you were at the mini talk on Tuesday night, you saw some weighted degree in the talk by Irene. And so I'm going to start with this kind of example and then expand on that. So first, we start with a weighted degree. So if, so I did not like that, the degree with weight alpha of P, so this is, if this is a weighted degree of P, where each variable xi has a weight, alpha I, say, it's a positive real number. Well, if you take minus this function, it's a valuation. So it's a valuation with value in the R negative and with the special value infinity. So with values in R negative and infinity. So I prefer positive numbers, so I tend to think of it in terms of degree. So where you replace min by max, so on. But if you want to think of it as valuation, then you have to put minus everywhere. Okay. To take some mean of negative number, I cannot do it, so I prefer to take some max of positive number where I see what I'm doing. Okay. So, in fact, I'm going to look at the subspace of valuation I'm going to consider is going to have this property. So they're going to take value in the negative real number, and they're going to be more or less of this form, but slightly more general. So let me define what all the valuation I want to consider. So expanding on this example more generally. So to each choice of F in the Tame group, I'm going to associate a subset of the space of valuation. And the idea is that I'm going to put, at the end, when I will put the metric, it will be a copy of R to the n-1. So we attach a subset that I will denote EF inside the space of valuation. Okay, so Vn is a space of all valuation with this property. The space of valuation with value in R negative and infinity, and it's always I consider my valuation up to positive scaling. So I consider that valuation and lambda the same valuation, where lambda is positive as the same. So I consider all my valuations are always up to scaling. Okay, if I put the weight 1 and 2 for my degree, or if I put the weight 2 and 4, I consider the same. It's just by a scaling of 2. Okay, so I consider the valuation is equivalent to lambda, the same one. Lambda is positive.
You want the value to be
I want what?
non-positive or negative? The weight has to be positive. Okay? The weight to be zero.
Yes, that's a choice to be made, and I choose to be strict. So it. Okay, so let me define this subset. So the E is for Euclidean, because I will put an Euclidean structure on this, and the name I give to this subset is the apartment associated to F. And the vocabulary comes because the inspiration for the construction, in fact, was from the theory of Tits building, where they have this funny vocabulary of apartment and chamber, and so on. And since the inspiration comes from that, we kept some of the vocabulary. Okay, so what's this EF? So for reasons that you will understand just after, in fact, I'm going to use not really F, but F inverse. So denote G is G1, Gn. These are the components of F inverse. Okay, so I'm going to use the component of F inverse. Pick some positive weight, so alpha 1, alpha n, some positive weight. Now you pick a polynomial, and you want to define a valuation, the value of your valuation for that. So for any p polynomial, well, you can write p as a monomial in x1, xn, but since g1, gn is an automorphism, this algebra is also the algebra generated by g1, gn. So you can write in a unique way your p as monomial in the gi. So you write p as a sum over multi-index of the ai, G1, E1, Gn, En, where I is my multi-index. Okay? And then, in fact, I'm going to define the weighted degree, but with respect to this basis for the algebra. So precisely, that's the following. So we define the weighted degree with respect to f with weight alpha of p. So it's a max over the support of my p. So for E in the support. So the support means the coefficient, the multi-index, so that the coefficient here is non-zero. Okay, that means that AI is not 0. And I take the max of the, so I take the degree of my, so I take E1 times the weight alpha 1 plus E2 the weight alpha 2. So it's a sum of the ek alpha k from 1 to n. I take the max of it. So this sum is a weighted degree of my monomial. The first one with weight alpha 1, the last one with weight alpha n. Take the sum, and I take the maximal for all monomials that appear really in my decomposition. So the ai are not 0. Okay, that's a definition of the weighted degree. Just the funny. So the previous one where you use x1, xn, and here I use another basis for the algebra. Something missing? This is I, and these are the exponent here, ei, en. Yeah, the exponent are here. This is the exponent. This is the weight. Good. So it's a degree, and if you take minus this degree, the same, you obtain your valuation. So my EF, that's the space of minus this weighted degree. So F is fixed. So F is fixed. So the inverse is fixed. So the GI, I use always the GI, and I vary the alpha. So this is something inside R n strictly positive. Okay. And remember that it's always up to scaling. Okay. So the weighted degree, the initial one, the usual one, correspond to the choice of f, the identity. So you have if you do that with f, the identity, you find the ordinary weighted degree, and this I call the standard apartment. And why the choice of using the component of the inverse is so that the action is more natural. So yeah. I prefer that the action is natural, but then when you compute one example, you always have to think that you have to take the inverse. So you have an action. We have a natural action of, in fact, a full group of automorphisms on valuation. So here I can even put odd kn on valuations. Just if you want to define, so you have G, which is an automorphism, and you want to compute that. So you want to act by automorphism on the valuation V. By definition, you precompose your P by G. Should be okay, yeah. I always have a doubt if I have to put an inverse or not, but I think not. No? Okay, I didn't put it in my notes, so I think it's okay. In general, when you put on this side, you want to put an inverse, but here you're acting on, in fact, on function, so it's okay. Yeah. Then, if everything is okay, you in particular, so this one I denote by mu associated to f with weight alpha when I see it as a valuation. I put a minus. So if you act by G, now it's in Tame. You act on my valuation, say f with weight alpha. the definition is made so that it's G times F with weight. So when you act, you just put the G in front. So it's natural from the point of view of the action. Okay. So for the moment, I define my space as a set, and now I want to put a metric on it, so that at the end it will be cat 0. Okay, so I'm going to put a metric on each EF. So you see that EF is parameterized by the weight. So I'm not going to think, so the weights are positive. I'm going to pass to the logarithm. So I take the logarithm of each one. So I think of each alpha I exponential of some beta I, and it's really on the beta I that I will put the metric. So we write alpha I is exponential of some beta I. The beta I now are in R. And remember that my valuation are always defined up to scaling. So if you scale your valuation, it's the same as scaling the weight. And since it's up to scaling, you can always, one way to normalize, to ask for the product of this non-negative real number to be 1. So we normalize by product of the alpha I equal 1. And so at the level of the logarithm, it's, the sum is equal to 0. So equivalently, sum of the beta I is 0. So you see that my EF, it is in bijection with the beta I in R1 such that the sum is 0. So EF is a space of the beta I, beta 1, beta n in Rn such that the sum is 0. And so this is an hyperplane in Rn, so it's Rn minus 1. And I put the Euclidean metric, I put this Euclidean metric, this distance coming from this Rn. Okay, so to compute the distance between two valuations with the same, with respect to the same basis, with the same f, but with different weight, just I pass to the logarithm, I look in Rn, I normalize so that the sum are 0, and I just put the Euclidean distance from this one. So this is Rn with
So when you think is going to depend highly on the choice of f? This normalization issue. So if EF and EG are going to intersect, then a priori the distance are not going to be the same.
yeah, but in fact, this problem is not a problem, because if yeah, in fact, that's the first lemma of the paper, that alpha is intrinsic. So if you have a f alpha which is equal to g beta, in fact, alpha and beta are the same up to permutation. So up to the order, they are the same.
Even with the normalization?
Yeah. I don't know why you have some doubt. You know. There are some more crucial problem in the construction. Yeah? Okay. Okay. So the first proposition is that by putting such a metric on each apartment, if I take as my space the union of all such weighted degree, so my X is a union over all F Tame of all these apartments. By putting this metric on each one, I obtain a metric on X such that each individual EF is still embedded isometrically inside the full X. So by doing this identification, if you're taking care of the intersection, you don't lose the fact that each EF stays Euclidean Rn minus 1 and is still isometrically embedded in my X. So this is a complete metric space, and each EF is isometrically embedded copy of Rn minus 1. Okay, so at least it's good. Yeah, so the problem, the fact that I put Tame is to have, if I don't put Tame, it's not clear that it will be connected. And so, in fact, so you do the same construction with hot, everything is okay, and then you have many connected components, and the connected component of my ordinary weighted degree, this is the one. Okay. And for cat 0, you need, you really want a connected space. In fact, you want simply connected. So that's the reason. That in some sense, it's natural to restrict to Tame because it claims as a connected component.
So in dimension 2, how does this compare to the 3?
So that's the next blackboard is what happened. So the plan now is to look at what happened in dimension 2, just to get a feeling of. So it's not going to be the Basser tree, for instance. It's going to be a tree, but not the Basser tree. So it's interesting. And then we'll look at some picture for n equals 3. And then I will try to explain why I can say it's a complete metric space, which is cat 0. Okay, that's a plan for the second part of the talk. Yeah.
Distance between two valuations that are not in the same part.
So okay, so you have so you have your so apartment. We put some triangle. We see a lot of triangle after that. So I have the first E identity, and then here I have E for another one. They don't intersect at all, but maybe I will explain that you have some ways of going from one to the other by a sequence, something like that. So in each, so it should be a triangle, no? So in each one, you know to compute, and so there is standard way when you put you have an union of metric spaces with identification because of the intersection here. So you want to go from this point to this point. You take any path from linking the intersection like that. So in each one, you know the length of your path, and you take the infimum. So the distance is going to be the infimum of the length of the path for all possible choices. And so it's a candidate to be the metric. It's not clear that okay, lots of things are not clear, and the proposition is not so easy. That's really the first section of the paper. Okay, so I don't comment more on that, but there is and it could happen that because you will see that the way two apartments coincide there are many possibilities, So it's not even clear that this fact that each EF is embed. It could happen that you have some kind of simplification, cancellation, and it could some points could identify some, but it's not the case. Okay, so let me maybe give you some picture for the case of two variables, where each EF is going to be a copy of R, 2 minus 1. So you have some copy of R, and I will show you that, give you a feeling that really this union of R is a tree. Not surprising, because the full valuation space is a tree. No? So case n equal 2. So you have this space. So this is my apartment identity. So it's a weighted degree on variable x1, x2. So here I have the ordinary degree where I put weight 1 and 1. Both variables are of the same degree, so that's the ordinary degree. That's the center of my line. Also, so it's really a copy of R. So the boundary is not here, but the boundary you can think that it's you put weight 1 on X, say, and you put weight 0 on the other one. So this one is not in my space, but it's naturally the boundary point. If I put the weight equal to 0, and here it's a way 0, 1. And for instance, if I take a weight D1, so you will see that when we put some integer d, comma 1, it's an interesting point because it's going to be a branch point of my tree. When d becomes very large, you go this direction. At the limit, it's really 1, 0. Infinity 1 is the same as 1, 0 because it's always projective. Okay, so that's the apartment associated to identity. So when I put d1, really what I want to, it's the valuation, so it's a minus the weighted degree with respect to the ordinary coordinate x1, x2 with weight d1 that I see up to scaling. So this is just a shortcut for that. Okay, now I want to draw the apartment associated to F, which is just a triangular map, x plus y square, y. Okay. So F inverse here is easy to write. It's x minus x squared y. So it's my G1 and G2. And I claim that the intersection is exactly this portion, where this portion where you put 2, 1, 2 because of the 2. So this is EF. Here you have the 1, 1 weight for F, but starting from 2, 1, and when you have bigger than 2, they coincide. After that, they separate. So to see that, you have to check that if you compute the degree of G1, I, and G2, J. So if you compute the degree of this monomial with respect to the degree with respect to F, it's just the weight. So with respect to mu F with weight alpha 1, alpha 2, is just you have only one monomial, so it's I alpha 1 plus J. Maybe I should put I1, I2. Yeah. Okay, so that's with respect to F, you express in terms of G1, G2, so it's a monomial, so it's easy. But now, if you want to express it in terms of the ordinary degree, so you have to replace, remember that G1 is that, so it's x minus y square to the I1, and y to the I2. And so you're going to develop that, and you see that if the weight of x is more than twice the weight of y, in fact, by the rule of the valuation, x to the I1 is going to be larger than all the other terms of your binomial expansion. And so, in fact, it's going to be the same as this one, and so they coincide. Okay, so it's exactly if x, the weight of x, so it's going to be, so if the weight of x is more than the weight, twice the weight of y, when you expand and you compute the ordinary degree, it's only x to the I1 which is relevant, and so it gives the same answer. So in this portion, they coincide, but if the inequality is in other direction, they don't coincide anymore, and you have different valuation. Okay, so you see that you have a branch point at each vertex of the form, at each weight of the form integers 1, and each time you take a triangular map, so if I replace the 2 by a d, it's going to branch at the d point. So here it will be the e associated to x plus y d y, or in fact you can even put any polynomial in d, and all the polynomial in d are going to branch here at this point. So another way to put it is that if I look at the action of this triangular map, x plus yd comma y, it fixes all these points, and it sends this one to this one. So you see that the fixed locus of elementary map, it has a fixed segment going to infinity in this direction, and then here it's kind of a rotation. So if you take a triangular one in the other direction, so you fix x and you do y plus x to the d, you're going to branch here at the 1d, where you're going in the other direction. And that's really the picture of that's a tree with branching point at each point of this form, and that's it. Yeah, like that. You branch again, branch again. That's the picture you should have in mind. And so to compute the distance I put passing to the logarithm, it means that the distance from this point to this one, the distance is log of d. So to compute the distance from this point to this one, you go from here to here, it's a log of something, and it goes from here to here, it's a log of something. You do all the sum, and you have your distance. Okay. Okay for dimension 2. Now, what really so it's really different from the Basser tree. No? In the Basser tree, you had a x, y in my notation from yesterday, and y, and the stabilizer of that was all the x plus polynomial in y, beta y plus gamma. So all the triangular one we are fixing this one with an action by rotation. Okay, but the full group was fixing just one vertex. Here, this full group, in fact, it fixes a boundary point, and each element fixes a segment, and the size of the segment depends on the degree. The larger the degree, the smaller the segment. So in this setting, the group is elliptic, and in this setting is more parabolic, so it's not the same kind of. Okay. So now I'm going to show you, draw some picture for n equals 3. And I will try to give you a feeling of the space of valuation, two apartments, what are the possible intersections. I will try to be more precise at this picture. Okay. we look intersection between apartments when n is 3. So you see that in the two-dimensional case, I had my apartment was really a copy of. So it's a simplex because it's a projective. So it's all direction in R2 up to positive scaling. So the picture here, the initial one, the space. So the weights are in R2. But they are positive, so it's really in the positive quadrant. And it's up to scaling, so I can go from here to here. Okay? And so this picture is really, this segment is really what I put here. And I said that I was putting the normalization product of the alpha equal 1, and it's not what I'm doing here to do the picture. So the normalization product of the alpha I equal 1 is good to define the metric. I will explain after that it's really the good way to put the metric to have the cat zero property. But to do the picture, it's simpler to ask for the sum of the alpha I to be 1 and to have the simplex. So that's the difficulty of the picture you make are nice, but they don't represent well the metric we use. Okay. So if I do the same kind of picture now in R3, I have the positive quadrant in R3, and I'm going to use the simplex in R3. That's going to be my space of weight. And so my space of weight is naturally a triangle, and that's why all my apartments are triangles, because I think in this way. Okay. So it's a triangle without the boundary. It's an open triangle. But yeah, the same here, when I draw my segment, I have the two extremal points. Here I have some natural points on the boundary. So here is my picture for one apartment. So let's say it's the apartment E identity in. So the weight on the boundary, this one. So my convention is to take 1, 0, 1, 1, 0, 0, and 0, 0, 1. So in the middle, you have the ordinary one with weight 1, 1, 1. So always, everything is up to scaling. So if you want to put 2, 2, 2, is the same. It's your choice. Okay, so I have another apartment here with respect to F, given Tame automorphism in case 3. And I'm going to try to draw the point here, which are identified with point here. So for the case of n equal 2, I put the picture like that, all in the same picture, because it was a small dimension, but here I cannot. So there will be a portion here which is identified to the one. If I try to draw it, I have to no, it's difficult. So I draw the picture like that. So something here is going to be the same as something here. So it depends on F. So let's start with let's start with the easy one. So if you take F, x, y plus z to the d, z. Okay, you just add a polynomial in z to y, and it's just going to depend on the degree, so you just can take the z to the d. Okay, so then I have such a line here, and here I go to 0, d1, and all this portion is the same as here. Okay, so what I mean is that if you are here in the apartment of the identity, and if you take the same weight for the apartment of this F, in fact, it's the same valuation. It's similar to the portion that was the segment which was in common in dimension 2. But if you are away from this zone here, you are distinct. So the crossing line is really this line with this. So it's really the weight of the second one should be d times, should be more than d times the weight of the third one. It's really similar to the first one. Okay, so that's the first one. Now, if I take f to be a monomial, so x plus a monomial in y and z, so say y to the n, then to the m. Now the line is going to be like that. So you have the point m10 here. Here you have the point n01, and the portion which is common is this one. So for this f, it will be this portion which is in common. And again, it's the weight of x should be larger than the weight of n times the weight of y plus m times the weight of z. And this is this condition, this linear condition. It should be away from. Okay, and now just to show you a last one. If I take the two together, so I take the triangular map, so I do x plus yn z to the m y plus z to the d z. Then, in fact, the common part is going to be the intersection. It's going to be just this. So that's the common part between the identity apartment and the apartment of this one. So you see there is a connection between having an intersection and the fact that the first choice of coordinate and the second one are you pass from one to the other by a triangular map. So that's what we should have in mind. And in fact, so if you believe that when you go from one to another one and they do intersect because they differ by a triangular one. And so if you want to go from one apartment to another one, you have to take a composition of triangular one up to permuting the coordinate. And it's more or less the definition of the Tame group. That any Tame automorphism, it's a composition of elementary map up. At each time, you can permute the coordinates using the linear group, which is in the definition. Okay, that's why you get the connected component, and you will not get it if you have the Nagata automorphism, which is not a composition of triangular one. He has this nice apartment, but it's another city, no connection. Okay, so that's at the combinatorial level, we understand quite well the intersection. So there is a special one if you have the line going from 1, 1, 1 and this one. There are some apartments that touch. So for example, I'm going to give you just this one. So if you're here, you have the weight of the form alpha 1. So the first two are equal, and the point here is 1, 1, 0. So when alpha goes to infinity, alpha 1 goes to 1, 1, 0. Okay, and this will correspond to the choice of f. Say so you take something like that. Y plus z to the d, x plus z to the d, z. So you see here it's y and x are permuted, and I put something in a polynomial degree d, and it will correspond to, if I put d here, they would have exactly this segment in common. Okay, so the common part between the identity apartment and the apartment of this f is exactly this segment where the D corresponds to the polynomial in Z I put here. So you see that it's not exactly triangular, but almost. No, so there is something triangular here. It's the fact that you have so this will be triangular. So triangular in general, you admit here something in Y and Z, and then only in Z, and then Z plus constant. But so it's particular in the sense that here I have no Y, it depends only on Z. So it's a especially nice triangular, or it's a degenerate triangular map. But at the level of the linear part, it's not triangular because here I have Y, I have the permutation. So at the level of the linear part, it's this one. So you also have it's not strictly speaking a triangular map. It's not two apartments coincide if only if they differ by a triangular map because of that, but it's not, well, you have a few exceptions. You have exception here, and you have similar exception here. And so we have a complete list. We understand the way that two apartments coincide. Okay. So that's at the combinatorial level. But now we have to understand from the point of view of the metric, what are the geodesics? And with this picture, it's easy to think that to go from this point to this point, the shortest path is this one, but no, because the metric is defined by passing to the logarithm. Yeah, question?
Is it possible the intersection or compact?
That's the intersection, huh?
Compact without being
No. So it's always you have a cutting line, and then it's everything away is intersection. So our intersections are always attaching to the boundary line. And okay, maybe a typical. Here I put only one monomial. So really the real triangular one will be of this form, the more general one. So here you have a sum of monomial, and so the intersection will be, let's make a last picture here. For each monomial, you have a direction, and so if you have several monomials, you're going to get something like that. So the portion will be, so if you have only the P, the intersecting locus will be like that. So away from this polygonal line, you have everything. And if you put the Q, it's only depend on the degree of the Q. So you can think it's Z to the D, and so you intersect with one line here going to the special point. So and then you have only this path. This is always unbounded. Okay, so that's the moment I want to show my picture. So I have to. Up. Okay, so the first picture is you have the identity apartment, so the standard apartment. So I didn't say, but for the action of the Tame group on my large space X, this apartment is a fundamental domain. Not exactly, in fact. The fundamental domain will be just this portion. So you have that, and then there is a natural decomposition in 6 parts. And when you act by permutation of the coordinate, in fact, you exchange these 6 parts. So really the fundamental domain is this that we call the fundamental chamber. So it's a six of the. Okay. Yeah. So the picture is all the line where you can change from one apartment to the other. So when you are in the white zone, you cannot go. You are in the apartment identity, and you cannot go right away to a neighboring apartment. But when you are on a line, there is some apartment, in fact, many apartments in branch along this segment, and so you see all the possible segments. So from 210 to 301, it's a kind of yeah. So I don't have the picture anymore, but when I put something from here to here, you see a lot of this line. And also there is a special line like that. And there is a line like that. And along each of these lines, you have infinitely many branching apartments with something in common, which is going to infinity. Okay, so you could think that the full space is a collection of Rn which are glued together along this zone. Okay, but then we have to think about the metric. And in fact, they are not glue along geodesic, because that's the second picture, that if you look at the metric, so here on the left, it's the same picture again, just I go far away, so on the boundary you see black because they accumulate. And in red and blue, I just chose randomly 2 of the cutting lines. And on the right, it's the same picture, but with the right metrics. The metric of an apartment is a standard metric of R2. So here it's R2, and I draw the same curves in the metric. So you see that the blue and the red are not geodesic, because geodesic are supposed to be line in R2. Okay? So you see that the cutting line passing through the corner, they stay lines. So these are the only ones that here, the straight line here, indeed are geodesic in the R2 matrix. In fact, it's if only if they pass through one of the corners. And as soon as you have a line going from one side to the other side, so it's a cutting locus. You can go from one apartment to the other, but it's not a geodesic line for my metric. So in fact, what we're really doing is we glue some R2 along some convex subset where the equation is of logarithmic nature. So it's not clear at all that it's going to work well. That's why the proposition is not so easy, because we do some gluing. If all the gluing were along polygonal zone, it would be easier, but it's not the case.
Why did you choose that metric after all?
Exactly. So that's what I had to explain is the 20 last minute. Okay, so thank you, Jasmine. Okay, so the main result of the paper with Piotr is that not only it's a metric space, but it's a cat-zero metric space. Okay, sorry. And let me state the corollary right away. Corollary, any finite subgroup F inside Tame K3. So here it's characteristic 0, and I'm n equals 3. Okay. So the previous proposition was for any k, any n. It's a metric space, but for cat-zero property, we need this setting. So any finite subgroup in Tame K3 and characteristic 0 is linearizable. So it means that there exists phi, another Tame map, such that phi f, phi inverse is inside the linear group. Okay, just so it's a cat-zero metric space. Any finite group has a fixed point. I look at the fixed point. I understand the stabilizer of my action, and then it's immediate. Okay, so it just really the cat-zero property is the main ingredient.
The definition works in any dimension, but the fact it's a cat-zero space.
Okay, so exactly. So yeah.
Do you expect this to be true in any dimension?
No.
It's not true.
Yeah. So okay, so how do you prove that a space is cat-zero? So idea of proof. So the cat zero condition, in fact, it's two conditions. One, you can think of it as two independent conditions, one global one and one local one. So the global one is that you need to check that it is simply connected. And the second one, you have to check the triangle condition on small triangles locally. So the same condition, but locally. So local non-positive curvature. Okay, so on the large scale, you just have to check this topological condition that it's simply connected, and then you just have to check at the local curvature, not for large triangles. Okay, so it's known as the Cartan-Adama principle. Okay, so for simply connected, that's why we need characteristic 0 and n equals 3, because we use again the Chestakov-Yurbebaev trick. So because we know something, we have an algorithm to reduce the Tame automorphism. Again, that's the same kind of proof as for the triangle complex. So it follows from Chestakov, Yurbebaev. Okay, and then the local one, and then we just have to check the local condition. So we pick a point on the standard apartment. It seems by transitivity of the action, you can just look at a point in the identity apartment. And you have to understand locally when you have so you are in your identity apartment, you choose a point, and you look at all the possible cutting locus passing through this point. So you look at all apartments you can visit in the immediate neighborhood of this point, and you have to check if there is a loop with angular metric. It's Euclidean, there is a notion of angular metric, and you want to check if there is a loop, so not in one apartment, but in many apartments, which is, if it is strictly less than 2 pi, it's going to be positively curved, and you're doomed. But if it is always more than 2 pi, it's exactly the condition. Okay? So it's just looking at a loop locally in your big complex of apartments, and check that you have no small loop.
So the loop is visiting finitely many apartments, you compute in
Each apartment, I compute the angle, and I do the addition, and it should be always 2 pi or more. Okay. Okay, so now, so that's a question of Romain. It will be, of course, we started by saying, okay, we're going to use the simplex metric, and we're going to do the trick, and we're going to check this, and everything is going to be fine. But no, if you use the simplex metric, you don't pass to the logarithm, you see some small loop. So I'm going to show you a small loop, which become exactly of length, which become a large loop with the right metric. No. So it's really the example that shows that it's a good idea to pass to the logarithm. Okay, so I give you a simple example. Where the small loop is going to be less than 2 pi, but the large loop is going to be much larger than 2 pi, and we have example where the large one is exactly 2 pi, so that it's quite sharp, the construction we made, it seems. So, example. Yeah. Yeah. What is what?
What is this 2 pi?
So it's I'm going to do it again here, this example. So I try again, and if the question is still there, ask me. Okay, so I want to look at the f is going to be x1 plus x2 q, x2, x3, and my g is going to be x1 plus x3 m, x2, 3. So I take two very simple elementary ones. This one depends on x2 and this one on x3. So they commute, And I'm going to assume that this m, the second exponent, is in fact a multiple of q. It's p times q for some p. And then I look at this picture. So I have map here, I have somewhere here, and I have this one. So here it's q1, 0. Here it's 1, 0, 0, 0, 1, 0. Here it's m01, and here it's 0p1. So this condition that m is p times q is to be sure that they intersect at, you have this intersection. Yeah? But really I'm interested in this point, m being very large, so this point going to this one, and this point, this q being very large. Okay, so for the picture, I don't draw it here, so that we see something, but morally, this point should be very close to this one. So it means that this angle here should be almost this one. So this one should be, if q is very large, and so m is also very large, this one is almost pi over 3 in the simplex metric, the bad one. And now I look at the 4 apartment. So I have 4 apartments, which are the identity, the apartment of F, the apartment of G, and the apartment of the product, which is FG or GF. It's the same because they commute. Okay, and now I look only at these 2 lines, so this one, and what is the other one? This one. Okay, so I start from here. So really, I'm at the point, and I'm going to look at a small arc. So this arc is in apartment identity apartment. It's not in the other one. And when I arrive here, this line means that I'm also in this apartment. So let's check. Q corresponds to F, so F. So when I'm here, in fact, I'm here. Before, it was not the case. Okay, so if I continue here, this point will be the same as this one. But here, I turn back, and I go back this way. So these red ones are in this apartment, but not in this one. This point was a common point, but not this one. So it's really a loop around this point, which is really injective. And I go on until I arrive to this one. When I arrive here, I'm here. So here, I turn back again, and I do that 4 times. Okay. That, here, I'm here, and I go back. And I'm here, and so this is my loop. So I have a loop around this point on each, so it's composed of 4 arcs. Each arc is almost pi over 3, so it's pi over 3 plus epsilon. The epsilon is as small as you want when q and m becomes large. And so you have 4 pi over 3 plus a little something for epsilon. So it's less than 2 pi. No? So it's too short. So if I use the simplex metric, which is the obvious one, I have some short loop, so I have some positive curvature. So it's no good. Now I pass to the logarithm to the R2 matrix that I put, passing to the logarithm of the weight. And then if you still have the picture in mind, the picture of the, so the line passing through the corner, which is the case here, they become parallel lines that you have the parallel lines, the vertical one, then you have this one all parallel, and then this one all parallel, depending if you pass through this one, and this one. And so in fact, these lines in the R2 metric, this one, and this one are all equal, and they are all pi over 3. So in fact, in the R2 metric, the good metric, this angle is always pi over 3, and here pi over 3, and it doesn't change when the point is moving. Okay, so you replace everywhere pi over 3 by twice. So you have 2 here, and now it's good. It's largely good, in fact. But we have some example where it was bad in the simplex metric, and where passing to the good metric, it's exactly good, it's equal to 2 pi, it's perfect. And it happens when you do the same kind of example, but you really put something depending on x2, x3 for one of the two. Yeah?
So I would have guessed, and I guess it's wrong, that because these commute, this might have been your extremal flat example, but it's not. So your other example, is it coming from a relation between?
No, it's coming when you put here x3 to the q prime. So, and it does not really commute, but it's a triangular map. When you compose the two, you have a triangular map. And so here you will have the triangular map. And so it's not exactly that commute, but...
so you don't magically detect relations, composition relations from...
all the small loop comes from a triangular map. When you have a triangular map, you have two ways to write it. It's one way to write it, another way. It's commute, but it's... you have something similar for all triangular maps. You want me to be more precise? I can be more precise.
No, I think I'm still hoping that there was some metric way to detect relations.
Okay, so maybe let me finish 5 minutes. I will make some comments on the higher dimension, and you will see that it's really a miracle. And since it doesn't work in a higher dimension, you cannot have a very conceptual argument to say it works. So it really seems like something unexpected happened here. Why is it K0? I don't know. So why we tried is because the idea comes from the Tits building for the linear group over QP set. They have some similar construction, but they look at basis of the vector field of a QP. They put some valuation, putting some weight on the basis, and very analogous construction. And there, the right metric for them is to put the logarithm of the weight. So we said, okay, let's try the same way. It works. Okay, so that's the way we had the idea. Otherwise, I mean, but then we were expecting that it should work in for 4 variable, 5 variable, and no, there is a problem. So I'm going to finish explaining that. So last comment. So it is known, in view of the corollary, in fact, we know that there exist in a higher dimension some example of non-linearizable finite subgroups. So there exist non-linearizable finite subgroups inside, in fact, hot K4. So it's not clear that the example is in Tame K4, but if you add one variable, it becomes Tame, that we know. So in fact, there exists the same example, in fact, if you add one variable in Tame K5, and so in fact in Tame Kn for any n larger than 5. Okay, so it's very specific. I can give you the example. So you take the finite group is G is the symmetric group Sim3. So it's a group with 6 elements. I give you the two standard generators. So the 3 cycle. So they express that in terms of A, B, X, Y. So that's just the variable. The 4 variables are A, B, X, Y. So the first one you just multiply Y and B by a cubic root of unity. Okay, so they're for sure, this one has order 3, no problem. And the second one is more complicated. You want something of order 2. So you switch B and A. That's order 2. And after that, you do something linear on X and Y, and a linear involution on X and Y, but the linear involution depends on A and B. So I give you that as a matrix. Okay, so it's the two coordinates here are linear in X and Y depending on the matrix, and the matrix is the following one, minus B cubed 1 plus AB plus AB squared, 1 minus AB, A cube. Okay? So you can check it's an evolution, it's linear, invertible, order 2, this, and it gives you a copy of the symmetry group of order 3 in the group with 4 variables, and they know that it's not linearizable. And if you add a fifth variable, it becomes tame. Okay? So the theorem cannot extend. It's not true that X, in the case n equals 5, you take the union of all the tame apartment. It cannot be a cat-zero metric space because otherwise, automatically, the stabilizers are fine and the proof of the corollary will work. Any f in tame K5 will be linearizable. It's not the case. Okay, so since I have this counterexample, it means that the in dimension 5 is not true, but the cat-zero condition, in fact, it's 2 conditions. So I don't know if the problem is that it's not simply connected or if it's not locally negatively curved or both. I don't know what breaks. At least one of the 2 breaks, I don't know which one. Just already it was a nightmare to compute locally for this 2-dimensional complex, and here I have to do it with object of dimension 4. Well, Piotr, he was ready to do it, but I don't, well, okay, maybe we'll do it someday. Okay, that's it, thank you. I realized I forgot to mention that there is the last preprint, in dimension 3, characteristic 0, X, the Tame group satisfies the Tits alternative using the cat-zero property. So we have it in this case.